Hi, everyone. I'm Nilou Sarvian, and I'm a fourth-year PhD candidate. My advisors are Matt Hurtgen, Andy Jacobson, and Maggie Osborne, and this is my Sloss Talk. So there are at least 2 global glaciations during the Neoproterozoic. It is hypothesized that the Earth was completely glaciated from pole to pole, including around the equator, for millions of years at a time. It's unknown how the Earth got so cold, but following these global glaciations was the evolution of metazoan life. So understanding what mechanisms led us into a global glaciation is important for understanding our evolutionary history. This is a plot of carbon isotopes through time in the Neoproterozoic. Interestingly, carbon isotope data show massive negative excursions throughout the Neoproterozoic, and that the values stabilize at relatively high values at about +5 per mil. These carbon isotopes may provide a clue as to what mechanisms drove carbon cycle perturbations and how the Earth's climate was tipped into these global glaciations. As there are multiple ways to generate a carbon isotope excursion, my research aims to utilize radiogenic and stable strontium systems to shed light on what is causing carbon isotope excursions during this time. Stable strontium is a relatively new proxy, and not very many people use it. However, it has great utility when used with radiogenic strontium. So, inputs to strontium in seawater are weathering and hydrothermal, which has both a radiogenic and stable component. However, the only output flux is through carbonate burial, which has a fractionation in stable space, but no isotope change in radiogenic space. So to reiterate, while radiogenic strontium can only tell us about the inputs, stable strontium can inform us about both the inputs and outputs. Therefore, stable strontium gives us a better picture of the full strontium model. Furthermore, carbonate burial is an important lever here as it preferentially removes the light isotopes. And please note these values here are for the Phanerozoic. So here's my data, and what's interesting to note is that the radiogenic values mainly hold steady, while the stable strontium seems to move synchronously with the carbon isotopes. Furthermore, the average value for stable strontium measured here is 0.374 per mil, so around here, which is higher than the average of the Phanerozoic, which is shown here by the dotted line. Also to note that these are the first stable strontium values measured for the Tonian. So my hypothesis for these higher values is that there was an increase in carbonate burial leading into the Sturtian glaciation. I've built a model this summer to better understand what could be driving these values, but I'm still working on fine-tuning it. But I can share qualitatively, here are some thoughts on what could be driving these excursions. If radiogenic values do not vary, there are 2 ways that one could get a variation in stable strontium space. 1, an increase in carbonate burial would drive the seawater values heavier, as we saw in my results. And 2, another way to do this is to change the fractionation factor, which some have hypothesized varies as a function of saturation state.